Hello, and welcome to my video series of algorithms. This is part 4 of Module 5, Divide and Conquer Algorithms. In this video, we will present the master's theorem. In the previous sections, we have presented several divide and conquer algorithms, such as merge sort, counting inversions, and the closest pair of points. All of these algorithms share the same time complexity of O(n) log n. This is because they partition the original problem into two subproblems, each of which is half the size of the original problem. Meanwhile, their divide and merge steps can be completed in linear time. In the video discussing the merge sort algorithm, we demonstrated that algorithms with these features run in O(n) log n time. However, not all divide and conquer algorithms follow the same procedure. Specifically, they might have different numbers of subproblems, and each subproblem may reduce the size of the original problem by a different factor. Additionally, the time complexity for the divide and merge steps may vary. In this case, how can we determine their time complexity? Here, we present the master theorem as a general approach for determining the time complexity of divide and conquer algorithms given the parameters of these three factors. Specifically, let A be the number of subproblems derived from a larger problem, B be the size reduction factor of the subproblem compared to the original problem, and C be the exponent of the time complexity for the divide and merge steps. In other words, the divide and conquer algorithm divides each problem into A subproblems, where the size of each subproblem is B times smaller than the original problem. Meanwhile, the algorithm can complete its divide and merge steps in O(n) to the power of C time. As a result, we can express the running time Tn for solving a size n instance of the problem as follows. Tn equals A times Tn over B plus O(n) to the power of C. Here, the first term, A times Tn over B, corresponds to the time required for the recursion calls. This is because each subproblem is B times smaller than the original problem and has a size of n over B. Thus, solving it using recursion requires Tn over B time. Since we have A subproblems in total, the overall time needed for solving all subproblems becomes A times Tn over B. The second term, O(n) to the power of C, corresponds to the time spent on the divide and merge steps. Given the parameters A, B, and C, the master theorem can determine the time complexity of the corresponding algorithm. A very important caveat to clarify here is that there are still divide and conquer algorithms that do not fit into this paradigm. For example, we assume all subproblems have the same size, while there are divide and conquer algorithms that split subproblems into different sizes. As a result, if a divide and conquer algorithm does not follow this paradigm and cannot be described using the parameters A, B, and C, we cannot use the master theorem to determine its time complexity. To prove the master theorem, let's first visualize the divide and conquer paradigm using a recursion tree. The root of the tree represents the original problem, which has a size of n. It is divided into A subproblems, each with the size of n over B. The divide step is represented by the dark blue arrows that go from the root to its children. Once the subproblems are solved, their results are merged to construct a solution to the original problem. The merge step is indicated by the purple arrows that go from the subproblems to the root. The divide and merge steps together, highlighted by the green box, can be completed in O(n) to the power of C time. Note that the time complexity is computed based on the size of the original problem, not the size of the subproblems. This means that the total amount of time spent on the first recursion layer is O(n) to the power of c. Now, let's follow this paradigm and go one layer deeper. In the second layer, the size of each subproblem is further reduced by a factor of b. Therefore, the subproblems in the second layer have a size of n over b squared. Since there are a subproblems in layer 1, and each subproblem in layer 1 is further divided into another a subproblems in layer 2. Layer 2 has a times a, or a squared subproblems in total. The divide and merge steps for solving each subproblem in layer 1 require O n over b to the power of c time, because the size of the subproblems in layer 1 now becomes n over b. Know that we have a subproblems in layer 1. The total amount of time spent on the second recursion layer becomes O a times n over b to the power of c. With the previous discussion, it is not hard to generalize the analysis to the ith layer of the recursion call. At the ith layer, the original problem will be divided by I times, each time into a subproblems. Thus, the total number of subproblems at the ith layer will become a to the power of I. Because the size of the original problem is also reduced by I times, each by a factor of b, the subproblem size will become n over b to the power of I. In this case, the divide and merge steps for each subproblem will take O n over b to the power of I to the power of c time. Since we have a to the power of I subproblems in total, the overall time spent on the ith layer becomes O a to the power of I times n over b to the power of I to the power of c. We can convert the time complexity to actual time by multiplying a scalar r. In this case, the actual time becomes r times a to the power of I times n over b to the power of I to the power of c. Simplifying the terms, it becomes r times n to the power of c times a over b to the power of c to the power of I. Now, we have determined the amount of time spent on the ith layer. So, how many layers are there in total? We know that the size of the problem is reduced by a factor of b with an additional recursion layer. Therefore, it will take log bn layers to reduce the subproblem size to 1, where we can solve them using brute force approaches in constant time. The total amount of time, Tn, is the sum of the time spent on each layer over all layers. In this case, we can write Tn as the summation from I equals 0 to log Bn of r times n to the power of c times a over b to the power of c to the power of I. Since the term r times n to the power of c is independent of I, we can factor it out from the summation. As a result, Tn can be rewritten as r times n to the power of c times the summation of a over b to the power of c to the power of I, with I going from 0 to log bn. Denote the summation as s, then Tn equals r times n to the power of c times s. Next, we'll determine s. Observe that the amount of time the algorithm spends on different layers forms a geometric series. The initial term t is 1, which corresponds to the time r times n to the power of c needed to construct the solution of the problem located at the root. The common ratio, q, is a over b to the power of c. To simplify the computation, we take the number of terms, m, as log bn, which is approximately the same as log bn plus 1 when n gets large. According to the rule of geometric series summation, when the common ratio q does not equal to 1, the sum s can be computed as t times q to the power of m minus 1 divided by q minus 1. Otherwise, when q equals 1, s is simply m. Now, to further simplify the term, we need to discuss the following three cases. First, when the common ratio is larger than 1, or c is less than log ba. Second, when the common ratio is less than 1, or c is larger than log ba. Third, when the common ratio is 1, or c equals log ba. In the first case, where the common ratio q is larger than 1, q to the power of m dominates the entire formula. Therefore, the sum is in the order of O q to the power of m, or O a over b to the power of c to the power of log bn. After a series of simplification, we obtain that the time complexity of the entire divide and conquer algorithm is O n to the power of log ba. Details of the simplification is shown in the slide. You can pause the video to go through the process. The step that is colored yellow uses the fact that a to the power of log bn equals n to the power of log ba, which is proven in the footnote. In the second case, where the common ratio q is smaller than 1, q to the power of m approaches 0 when m grows large. As a result, s is dominated by t over 1 minus q. Since t and q are both constants, s is in O1. Therefore, the time complexity of the entire divide and conquer algorithm is O n to the power of c. In the third case, where the common ratio q equals 1, we have s equals the number of terms m, or log bn. In this case, the time complexity of the entire divide and conquer algorithm is O n to the power of c times log bn. Now, let's summarize the master theorem. When c is less than log ba, the time complexity of the divide and conquer algorithm is O n to the power of log ba. When c is larger than log ba, the time complexity is O n to the power of c. Finally, when c equals log ba, the time complexity is O n to the power of c times log bn. Let's use the master theorem to determine the time complexity of merge sort as an example of its applications. For merge sort, we divide the original problem into two subproblems. Therefore, A equals 2. The size of the subproblem is half of the original problem. Therefore, B equals 2. Finally, its divide and merge steps can be completed in linear time. Therefore, C equals 1. In this case, we have C equals log BA, which corresponds to the third case of the master theorem. Hence, the time complexity of the algorithm is O n to the power of c times log bn. Plugging in the values of b and c, we obtain that the time complexity of the merge sort algorithm is O n log 2n. Thank you for watching, and see you next time.